My name is Nima Moshiri, and I'm an assistant teaching professor in the Department of Computer Science and Engineering at UC San Diego. I'll be presenting about ViralMSA, which is a tool that enables the rapid multiple sequence alignment of viral genomes. First, what is multiple sequence alignment? Imagine I have these patients, X, Y, and Z, and when these patients come to the clinic, I could theoretically sequence their viral samples and collect a viral sequence from each of these patients. So this is the viral sequence of X, Y, and Z. You'll notice that these sequences look very similar, but they're a little bit off. They don't quite line up, but you can imagine if I were to stick in a few spaces, gaps I'll call them, I can make these line up much better. So multiple sequence alignment is important for detecting sequence homology. It's important to be able to get public health or epidemiological information from these sequences. Imagine I have n individuals and each of their sequences is length k. The multiple sequence alignment problem solved optimally is big O of k to the power of n. This is extremely slow, especially as n increases rapidly, which it does in the case of a pandemic. So heuristics have been developed that can solve this problem, at least heuristically, much faster. Currently, most of these heuristics are big O of n squared k plus big O of k squared n. This is a much better step in the right direction, but unfortunately, for the case of COVID-19, this n squared term is still far too large. In the event that virologists have assembled a high confidence reference genome, as is usually the case pretty early on in an epidemic, I can use the reference genome to help speed up multiple sequence alignment. I can do a pairwise alignment of each of my queries against the reference genome independently and potentially simultaneously. So for each position in each of my query sequences, I can figure out where in the reference genome it best fits. And then using these individual pairwise alignments against the reference genome, I can take the positions of my reference genome and use them as anchors with which to combine each of the pairwise alignments into a multiple sequence alignment. I performed a benchmarking experiment in which I compared ViralMSA against the current state-of-the-art multiple sequence alignment tool, MAFT, across different viral datasets at different dataset sizes. So on the horizontal axis, we have number of sequences, and on the vertical axis, we have execution time in seconds. And consistently, ViralMSA scales better than MAFT and is generally orders of magnitude faster. To assess the accuracies of the alignment tools, I took the viruses that had ground truth multiple sequence alignments and I computed pairwise distance matrices of the ground truth alignments as well as distance matrices of the estimated alignments, and then I performed a Mantel test of correlation across the estimated and true multiple sequence alignments. On the left, I show Spearman correlation, and on the right, I show Pearson correlation. A value of 1 indicates perfect correlation, -1 indicates perfect anti-correlation, and 0 indicates no correlation. We see that both tools consistently have extremely high correlation, meaning both tools are consistently estimating very accurate multiple sequence alignments, with MAFT consistently doing better than ViralMSA. ViralMSA can be found on GitHub as an open source Python project.